In this video, we'll be looking at our problems 5.23, 2.5, and 2.7. This will help for our upcoming quiz. I'm going to begin with 5.25 and then do 5.27 and back down to 5.23 as we did the 5.23 in class. 5.25 is dealing with dogs. A study investigated whether dogs change their behavior depending on whether a person displays reliable or unreliable behavior. Dogs were shown two containers, one empty and one containing a dog biscuit. Experimenter points to the two containers. If the treat was shown on the first trial, 16 of the 26 dogs followed the experimenter's cue on the second trial. However, if the experimenter misled the dog on the first trial, I know some of you are sad already, 7 of 26 dogs followed the cue on the second trial. Test to see if the proportion following the cue is different depending on whether the person exhibited reliable or unreliable behavior. So we are interested in a proportion. That's our parameter. And we're going to have two groups, a reliable and an unreliable behavior. All right. So we can have a couple p-hats here. For our reliable behavior, our p-hat was 16 of 26. P-hat for our reliable, 16 out of 26. Our unreliable was 7 out of 26. P-hat for our unreliable, 7 out of 26. Alright, previously to find this difference, we would simply fire up stat key and click some buttons, and stat key would do some randomization, and that would be it. Now we're using this new normal approximation. Well, we will begin by using our same hypotheses testing procedure. We're going to state a null and alternative hypothesis and define a parameter. So our null hypothesis, our default null, is these two groups will be the same. The proportion of reliable response, the proportion of dogs who follow the reliable person will be the same as the proportion who follow the unreliable. An alternative that we're trying to show would be that the reliable cue produces a higher proportion than the unreliable. And P is the population proportion of dogs who follow a cue. All right. We have the reliable cue group and the unreliable cue group. The P is the population proportion of dogs who follow a cue. Well, instead of using stat key, we're now going to use this standard normal curve. So we're going to be using this our new normal model, and what we need to find is where this particular observation falls. Well, we know that to say that PR is greater than PU is the same as saying that PR minus PU is greater than 0. From here to here, I simply subtracted my proportion of the unreliable on both sides. So we're looking at a difference in proportion. So I want to take this particular difference up here. So my difference will be P hat R minus P hat U. So that is 16 over 26 minus 7 over 26. And that is 9 over 26 and 9 over 26. This is roughly 0.346. So that's pretty substantial difference, 35%. We don't have a ton of dogs, 26 in each group. So is this enough? Could this difference have happened by chance? Were these 23 dogs that followed, they were just going to follow? It just so happened that they were shuffled out like they were. we can now conduct our test using our normal approximation. We need to find a z-score. We need to know where this thing is going to fall on our normal curve. Well, our z-score is equal to our statistic, our sample statistic. You can find this directly on your chart. Sample statistic minus our null mean, or in this case null proportion, divided by the standard error. Our sample statistic in this case is the 0.346. Our null mean, well, our null is that they're equal, so the associated statement is that PR minus PU is equal to 0. So that's what goes here. When we're dealing with our differences, this null will always be a 0, so it'll just be the sample stat at the top. And our standard error is given to us in the problem as 0.138. So what they're saying is if we were come here, 0 is going to be the mean, and our jumps will be 0.138. So instead of +1, it's 0.138. Instead of +2, and I'm just going to write it down here so it's not crammed up, 2 times 0.138 is 0.276, and 3 times 0.38, 0.138, pardon me, would be 0.414. So this 0.346, it's pretty far out there, all right? You can see it would be somewhere between 2 and 3. Well, we can do this division to find out. 0.346 divided by 0.138 is equal to 2.5. So our observation of 3.46 falls at about 2.5 standard deviations. That would be right about here. This is a z of approximately 2.5. We're interested in the p-value. We're interested in that or more extreme. We're interested in this area over here. Okay, that's the question. What is that area? Because that is our p-value. P-value is that area. Now we're simply going to find 2.5 on the chart. So I come to my chart and I find 2.5 on it. So it's going to be on the second page. Here's 2.5. We have 0.9938. 0.9938. So that's telling us that we have 99% to the left. Therefore, the percent to the right would be roughly 0.01. It was actually a little bit less than 0.01, but we're just going to round it to that. So our area is 0.01, and that is the p-value. Okay. Well, we're ready to conclude now. Since our p-value is less than alpha, the problem stated our alpha was 0.05. 0.01 is less than 0.05. We reject. P-value low, reject the whole. We reject H naught. The data suggests HA. And our HA in context, just change this to the words here. The proportion that follow the reliable Q is greater than the proportion that follow the unreliable Q. What do you know? Being honest is meaningful. The data suggests the proportion of dogs who follow the reliable Q is greater. Than the unreliable. All right, number 27. Smile leniency. Data 4.5 on page 293 describes an experiment to study the effects of smiling on leniency and judging students accused of cheating. Exercise 5.23 on page 361 shows a dot plot reproduced in figure 5.12 of a randomization distribution of difference in sample means. The relevant hypothesis is the two groups are the same, and the alternative is that if you smile, it's going to be greater than if you don't smile. Kind of makes sense. If you're smiling, you're sort of indicating, I don't care. And if you're not smiling, you have a serious face, you look like you're sad, so you're going to get less punishment if you look showing some contrition. All right. It says this distribution is reasonably bell-shaped, and we estimate the standard error of the differences in means to be about 3.93. For the actual sample in smiles, the original difference in the sample mean is 0.79. Use a normal distribution to find and interpret a p-value for the test. This time I'm just going to jump directly. We already have our hypotheses. I'm just going to jump directly to calculating the test statistic and using this particular standard error. All right, so our z score for this situation, again, our z is the statistic minus our null over our standard error. In this case, our statistic, the stat, is the difference, and they tell us that that is 0.79. We know since it's a two-group situation that our null is going to be 0, and they're telling us that our standard error is 0.393. Well, if we bothered to draw our normal curve, this standard error is roughly half of that. Okay, this is going to be 2 jumps out. 0.39 times 2 would be 0.78, and that's a little bit short of this. So this z-score is going to be a little bit greater than 2. This is 2.01. So what we want to know, when the z-score is 2.01, we want to know what is that associated area. So back to our table. 2.0 is this, so 2.01 is 1 more over. 2.01 is 0.9778. 0.9778. This is the area less than. All right, we want the area greater than. So the probability of getting a z-score greater than 2.01 would be equal to 1 minus that number. Because remember, this is the area to the left. 1 minus 0.9778. As I said before, just make 9s. So that would be 0 in the first position, 2 in the second position, 2 in the third position, and here I'm going to make a 10. 0.0222. This is approximately 0.02, which is 2%. So again, p-value is low. We'll use our default alpha of 0.05, and we're still ready to reject. Since p-value is less than alpha, that is 0.02 is less than 0.05, we reject a-naught. The evidence suggests the mean for smiling is greater than the mean for not smiling. That is the mean punishment. That is to say that if you get in trouble and you're smiling, if things are going to be worse for you. Makes total sense. Okay, back to 5.23, which we did in class, but if you've forgotten, then this will be a decent review. We're talking about studying for tests. There was 2 methods for studying. There's 2 methods for studying. One was reading side by side, and the other was a self-quiz. The early part of the study says that the self-quizzing has been shown to be better in many situations. Cognitive science consistently shows that one of the most effective studying tools is to self-test. That makes total sense because you're going to have to take the test. That's how you're being measured, so you're practicing exactly like you would do it. So when you're studying, self-test. All right. We got a couple of proportions. We have for our reading group, the proportion of success was 15%. So that's a p-hat. P-hat for our reading group is 0.15. And we have our study group, our self-quiz group, I mean to say, is 0.42. So the p-hat for the self-quiz is 0.42. Okay, we are testing the hypotheses. Again, we have two groups, so our null would be that the two groups are the same. P for reading equal P for self-quiz. I'm going to change up this order because of the way I did it in class. I'm going to put the self-quiz on the left and the reading on the right. It doesn't matter. That would change which tail the test is. That's all. Our alternative hypothesis is the proportion for the self-quiz is going to be greater than the proportion for the reading. Stated another way, the difference would be the self-quiz minus the reading is greater than 0. We're going to be looking at a right-tailed, as we have in all of these. All right, so we're looking at our difference. P-hat of self-quiz minus P-hat of the reading is 0.42 minus 0.15. That is 0.27. And I said in class we didn't have the sample size, but we actually do. It says it's 118 college students. So that's a pretty big sample, almost 60 in each group, and we had to almost triple the difference. So this just on the surface feels like, yeah, the self-quiz is really going to beat the reading. We have almost triple the difference, and 60 were in each group. That feels like it's going to be a whole lot. All right, well, here we come with our z-score. So z is the statistic. That's our difference. Minus our null divided by the standard error. In our case, our difference is 0.27. Again, the null difference is 0. And our standard error from the problem is stated to be 0.07. So 27 divided by 7 is 3 6/7, 3 point something. Well, looking at our curve, we only talk about the 3. We're talking about 4. In fact, this normal curve I don't like. It does. At 3 we should basically be at the line. 4 greater than 4. All right, this is a z approximately 4 out here. The area out here is virtually 0. The probability is approximately 0 to be greater than that. It's not even on our, if we bother to look on our table, it's not on the table. So there is virtually no chance to get that difference if indeed they were the same. Lots of evidence against. We're ready to conclude. Since our p-value is very low, p-value is less than alpha, that is approximately 0 is less than any alpha, our default 0.05, we reject H0. Data is very compelling. The evidence strongly suggests self-quiz beats self-quiz better than rating. Again, I should have mentioned the proportions in here. The proportion for the self-quiz greater than the proportion for the rating. You get the picture. Proportion of problem, percent of problems we got correct. Score on the test. All right. That concludes this video.